In the previous video, we highlighted how while the concept of mean deviation allows one to estimate the spread of the data, but has mathematical limitations. In this video, we will see how a more robust method of estimating spread of data is widely used in statistics. The concepts of variance and standard deviation are discussed here with less focus on the formulas and higher focus on the implications of these numbers. Towards the end, we will also discuss the coefficient of variation briefly, since these are metrics that often pop up in business reports and on various dashboards. The goal is to provide you with a simple way to compare variability across different datasets and to communicate the differences more meaningfully. As discussed earlier, mean deviation finds the average of deviations using absolute or positive-only values of the distance. However, that approach runs into trouble with more complex distributions and does not play well with the calculus needed for estimating likelihoods for forecasting or distributions. Moreover, while we assume a two-dimensional aspect to deviations, there could be many reasons as to why the value deviates from the mean to begin with. The method that addresses both these concerns is one of taking the square value of each deviation instead of taking the absolute value. This preserves the size of deviations in a way that works cleanly in later statistical methods. The mean or average of these squared deviations is called the variance, and it is expressed in a higher dimension of units. To visualize this spread on a two-dimensional number line alongside the mean of the variable, we take the square root of the variance to obtain the standard deviation. Now we can read the spread in a two-dimensional space without sacrificing the importance of other factors that could be associated with the deviations in the first place. Variance is the technical name for the mean of the squared deviations, and its value is always reported in squared units, which can feel abstract. For example, if you are measuring a variable in weeks, the variance will be in squared weeks, which is not something you can easily visualize or discuss with a manager. Standard deviation is simply the square root of that variance, which puts it back into the same units as your original variable, making it much easier to explain and apply. In practice, both numbers describe the same underlying spread, but for everyday business interpretation, you will usually talk in terms of standard deviation, because it maps more naturally to the data values you see. To reiterate, the variance mathematically embodies the shifts or deviations in more than one dimension. However, from a business application perspective, this nuance can be more confusing than clarifying. That being said, it is also, therefore, critical to interpret standard deviations from the mean more carefully when making decisions based on how a variable is distributed. If you had the data for every observation within a population, you can use the full observation count, n, in the variance formula. More often, particularly in business settings, you are working with a sample, which is just a subset of a larger population, and that situation requires a small correction using n-1 in the denominator. Without getting too technical about this, just remember that if you have a really large sample size, the variance will not change significantly, regardless of whether the sample or population formula is used. But if you have smaller samples, adjusting variance correctly matters. Using the population formula on a small sample reduces the calculated spread. This implies that you might end up being more confident than necessary in your hypotheses testing, or forecasting, or decision-making. Default to using the sample formulas as a protection against underestimating variability and making costly choices based on overly tight-looking data. And if in doubt, ask the report writer or data team presenting the numbers which specific formula was used and why. You will be surprised at how often this little nugget gets overlooked in the real world. Revisiting our example from the earlier video about a sample of weekly sales for 10 weeks, let us compare the sample's standard deviation values with the previous mean absolute deviation value and the population standard deviation value. With the sample size adjustment, we find that the sample standard deviation is 4.78 units. This is a much higher spread than our original simple mean deviation value of 3.8. Without the sample size adjustment, we would still get only 4.53 units deviation. But what does this mean in business? With a sample standard deviation of 4.78 units and a mean of 26.2 units, we can say that the normal range of sales each week lie within the 4.78 unit interval on either side of the mean. In regular terms, we can expect sales per week to be between 21.4 and 31 units. Here's a caveat to remember, which we will cover in more detail in the next video. The standard deviation creates probabilistic intervals of expected sales per week. The basic interval we just calculated, between 21 and 31 units per week, is associated with a specific probability of occurrence and is not an absolute guarantee. Decisions hinging on treating these ranges as absolutes are often erroneous and lead to unmet expectations in reality. The last important concept we will cover in the realm of variability is the coefficient of variation, or CV. This metric takes interpretation of data distribution a step further by relating the standard deviation to the mean, in percentage terms, so the units cancel out. Because it has no units, you can compare variability across very different datasets, such as age in years and revenue in dollars, without mixing scales. In the simplest terms, it takes the ratio of the standard deviation and the mean to determine if the data values are closer together or widely separated. In our weekly sales example, the mean is 26.2 units, and the standard deviation is 4.78 units, which yields a coefficient of variation of 18.24%. This means that the spread is relatively modest, and the sales per week are truly comparable and consistent, or homogeneous in characteristic. If the CV is closer to 100, check the sources of the data again, to ensure that the collection and organization of the data is not hiding biases about the characteristics of the variable. This idea helps you compare the relative stability of different markets, products, or processes using a single unit-free number. Variance and standard deviation together tell a story about how tightly or loosely your data values cluster around the mean, which is another way of reading risk. A small standard deviation suggests that outcomes tend to sit close to the expected value, making planning more straightforward, while a large one warns that reality could deviate more sharply from your forecast. Using the sample corrections keeps you honest about how much you really know from limited data, avoiding the trap of overstated precision. The coefficient of variation then lets you step back and ask which datasets or business areas are relatively more or less stable. For instance, if weekly sales have a low CV, but the weekly revenues are showing a very high CV, it might be worth investigating what other factors are causing larger shifts in the revenues. As you move forward, treat these measures as narrative tools that translate numbers into clear guidance on where caution, contingency plans, or bolder moves might be appropriate. Variance, standard deviation, and the coefficient of variation turn a simple mean into a richer, more realistic view of your data and its business impact. When you are working with samples, using the correct formulas helps ensure that you respect the uncertainty in your values instead of underestimating it. Standard deviation keeps the measure of spread in familiar units so you can discuss it easily with stakeholders, while the coefficient of variation lets you judge which variables are relatively more volatile or more stable. As you apply these ideas, aim to translate each number into a plain language story about risk, consistency, and confidence in your decisions. With that mindset, these statistics become practical tools for better choices, rather than abstract math in a book or a pretty dashboard on a slide.